Hello everyone. So in today's lecture, we're gonna keep talking about one important machine learning tool called classifier. And big little bit review what we learned last class. Last class we talked about the first classifier, which is the perception algorithm. And also at the end of last lecture, we talk about a famous algorithm is called the maximum margin classifier. That perception algorithm, we want to minimize the cost function. Recall this method is minimize. We want to minimize negative. This is the cost for misclassified cases with omega is W for I belongs to V. We want to minimize this one. So, and this set V is the set of the misclassified cases. In other words, yi and the classification label are different cases, so less than 0. Okay. So here the restriction is we want to minimize this as a cost. And on the other hand, maximum margin classifier, we impose another, instead of restrict the less than 0 here, we propose another constraint that yi omega xi plus alpha. So this classifier, we have the alpha now, and we restrict our not only greater than 0, less than 0, but we require it's greater than 1. Okay, so this is also called a we want to minimize the length of the omega w vector subject to this constraint. So this is also called hard. This is also called hard margin classifier. Also called hard margin support vector machine. SVM. In other words, the solution for the hard margin classifier gives us, like, for example, if we have the linear separable case, we have the black cross label and we have the blue circle label. Okay, suppose these two cases, these two classes can be well classified. Okay, so the hard margin not only gives us the decision boundary, but also restrict this margin, impose this margin distance. Okay, so that's the hard margin support machine. And in today's class, we're gonna introduce one more classifier, which is called soft margin SVM. In today's lecture, we're going to talk about soft margin SVM, support vector machine. The reason why we need this one is, so actually the first two classification algorithm is not perfect. It's not in practice. We hardly have the perfect linear separable cases. For example, if you recall our first class example, yes, for example, in most of the cases in real applications, the class we want to classify, they are not perfectly separable, perfectly linear separable. You cannot find a line that can clearly cut, because no matter which line you use, there are some labels will be labeled as green on the left side and blue circle on the right side, no matter which line you use. So that's the that's the problem for the hard margin support vector machine. So problems in hard margin support vector machine is this will fail problems. Hard margin support vector machine will fail to work if data is not linearly separable. Okay, that's the first drawback. Second, is also very sensitive to the outliers. Hard margin support vector machine is sensitive to outliers. And in most practical cases, applications, we're gonna use the classifier called the soft margin classifier. Okay, so here is one example. In this example, this is the hard margin support vector machine gives us a classification boundary. Okay, so that's a solution which also impose the maximum margins the largest margin we could have separate away from this decision boundary. But actually, if you just add one more point, for example, you just add a blue dot here. Suppose you add a blue dot here. Okay, so the new decision boundary will become to this one. So you can see there is a big shift, rotation from this dotted decision boundary to this one due to 1 point. The change due to 1 point. Okay, so motivated by this, we're gonna introduce the soft margin vector machine. So which will allow us, so as you can see, the maximum margin SVM, any data points cannot cross these margins. So that's what is this algorithm is defined. Your dot cannot be inside the margins. But for the soft SVM vector machine, it allows us to have some few points on each label. Each label can cross the margin, even cross the decision boundary. So how this can be imposed? This is imposed by introduce some slack variables. For example, we can allow some, for each point we can allow some so for each given omega, right, we can have the boundary. So the actually the margin width is decided by this 1 over w, the length of the 1 over w. Given this 1 over w, some points will be cross this margin, okay? And this is, we're gonna have some slack variable. Okay, for example, this point, we're gonna have the slack variable Xi 3. Okay, this is very large one. Let's see how we're gonna introduce. So actually, by introducing the software margin support vector machine, we need to redefine the margins. This is because for the software vector machine, we don't have the clear, because it's not a linear separable, right? So we don't have a single line within some amount of the range, no point across the margin. So here we're gonna define our margins. So here in the software support vector machine, the margin is just equals to is 1 over omega. Okay, in hard support vector machine, the margin is defined by the minimum distance between the decision boundary and the label point. Okay, but in the soft machine, we use the margin to be defined by this way. Okay. So, but we do not also want to overuse this slack variable. For example, some variable, if we give too large slack variable, we can misclassify too many, right? Too many. So we need to give some restrictions to this slack variable. So how do we impose these restrictions on these slack variables? Okay, so to prevent abuse of slack variable, we need not only we need to recall the heart of support vector machine, we minimize this target function with this restriction, but now we not only we want to minimize the margin, not only we want to minimize this margin, but also we want to so we want to minimize not only the margin, but also we want to give some penalties. So you can think this is the penalties for the slack variables. And for sure, this slack variable are positive. So from 1 to n, and we have some constant term. Okay, maybe like give you some note. So you can think this term is a penalty for large slack. Okay. And we want to minimize this problem to find the omega, but also subject to yi multiply. We want the label with had the same alpha. Okay, this should be greater than. Recall this in the hard vector machine we want it greater than 1, but here we want it to be greater than 1 subtract Xi I for all I for each data point for I from 1 to n. Okay. Also, we need to give restriction that this slack variable should be positive, it should be non-negative. So this is the algorithm for the soft SVM classifier. Okay, and also this C is called a regularization hyperparameter. And in your lab and homework, I think you will have the Python implementation in sklearns to implement this method. What all you need to know is you need to tune this parameter. Okay. That trade-offs. So when you apply this software SVM, we need to tune this cost constant C. Okay, so what this C really represents? So when you do the cross validation to tune this C. Okay, so I will give you a table. If we have the small c means small cost here, right? Small cost, small penalty for the large slack. So we will have big margins. We will have the maximum margin 1 over W. Okay. When we have big C means we have the high penalty for the large slack variables. So which means we give the big penalties for the large Xi, like a Xi3 in this case. So in other words, we wanted to have the slack variable to be small. So keep this big C will keep most slack variable small or 0. And later I'm gonna give you some example. So that's the first differences between when you choose big C or small c. Okay, and when you have the small c, you give the small penalties for the variable cross. You give a small penalty for variable cross the margins and cross the margins, right? So in other words, you're gonna give very big large margin. So you're gonna have large margin, and so you could have underfitting data. So it could had a risk underfitting the data. Okay. You could misclassify training data, much training data. Because you have a small c, you have the very wide margin. You're gonna have wide margin, and you don't have many cases that cross the class decision boundary. Okay. Also for the big C, so another thing you can think is you have a small c. If c is 0, it's basically the soft, it's a hard support vector machine, right? So you could have the underfitting the data, okay? And for the large C, you have the overfitting. So which means you could have very narrow margin, and you could have a lot of the cases cross the decision boundary. So this give us the overfitting, okay, which means it did very good job in training, but did bad in test data. Okay. Another difference is between big C and the small c is the outliers. So for the small c, we are quite less sensitive to the outliers. And for the large C, it's going to be very sensitive. Very sensitive. Also, another difference is the decision boundary. Decision boundary. This will be more linear. If you have the 2D case, the decision boundary will be more linear. Or you have more dimensional case, it's more flat. Your hyperplane is more flat. And with big C, you have more nonlinear case. But right now we focused on our case to be only the linear decision boundary, like a line here. But at the end of the next topic, after we introduce the soft support vector machine, we're gonna introduce how to introduce the other features based on the current features, and introduce this nonlinear decision boundary. So here I will give you one more example here. Okay, so in this plot, we can see there are 4 examples with uh, different values of c. As you can see, if you can think about this cost function and this slack, because big cost will encourage the smaller slack variable, right? So which one do you think is a case with a large c, and which case is a small c? Think I'll pause here for a minute and you can think about it. So you can think the slack variable is you can think the slack here. You can just think slack is a money, or you can think it's penalty or money you spend, can be spent, need to spend for to buy permission for a sample point to enter the margin to violate. So the further a point penetrates the margin, the bigger fine you have to pay. We want to make the margin as wide as possible, but we also want to spend as little money as possible. So if we can regularize, if our regularization parameter c is small, it means we are willing to spend lots of money to violate, so we can get a wider margin. Okay. And if c is big, it means we have cheap cost to pay the ticket to enter for the violation. So we don't pay much violations. So in this case, we will have narrower margins. So in this case, we will have the large c. So largest c. So this one has large c. So this one gives the largest c. This one gives the smallest c. Smallest c. So for small c, we encourage the large slack. So yes, so if we have the small c, we have large slack. For example, here we have a variable. Here we have the very large slack. Okay, so for small c, we could have we have the wider margins, so that the point can cross the boundary, decision boundary, to be labeled as blue. And when c is large, on the other hand, c is large, we have, so large c encourage small slacks. Okay, so we don't have this large slacks in this case. For example, the largest one is here. Okay, we have the relative small slacks, so we have the narrower margins. So that's C. Okay, so that's basically about the soft support vector machine.